Redox reactions. Redox is short for reduction and oxidation. The two processes involved in these reactions. Reduction and oxidation can be defined in terms of three changes: specific elements, oxidation states, or electron transfer. Today we will only be looking at the second one. An oxidation state is the apparent charge of an element, and to determine the state of an element, you have to take a look at the 10 commandments of oxidation states. When looking at a reaction, telling oxidation and reduction apart is simple. Oxidation occurs when the oxidation state goes up, and reduction occurs when the oxidation state decreases. So now, let's look at some examples. First, how do you use the 10 commandments of oxidation states to determine the oxidation states of elements in a compound? Here's an example. The first step you have to take is look at the 10 commandments and determine which rules apply. In this case, rule number 5, rule number 6, and rule number 9 apply. Rule number 5 tells us that when hydrogen is bonded with a non-metal, its oxidation state will be +1. And rule number 6 tells us that oxygen will always have an oxidation state of -2. That leaves us with the oxidation state of carbon. To find the oxidation state of carbon, we have to look at rule number 9, which tells us that for a neutral molecule, the oxidation states add up to 0. This means that once we add up all the oxidation states, we should get a 0. Because no rule applies directly to carbon atoms, we can assign an X to it. Now, because we have two hydrogen atoms, each with an oxidation state of +1, here we write +2. And because each oxygen atom has an oxidation state of -2, and we have 3 oxygen atoms, we subtract 6. If we solve for X, we get that the oxidation state of carbon should be +4. Let's look at another example. In this case, we're talking about a polyatomic ion. And according to rule number 10 of the commandments of oxidation states, the oxidation states of a polyatomic ion always add up to its charge. In this case, the charge is -1. So we know it will add up to -1. Oxygen, according to rule number 6, always has an oxidation state of -2. Because no direct rule applies to nitrogen, in this case we assign an X to it. And because we have 2 atoms of oxygen which has an oxidation state of -2, we can subtract -4. If we solve for X, we get the nitrogen has an oxidation state of +3. Now, how can we use this to differentiate between oxidation and reduction? To determine which element is being oxidized and which element is being reduced, we once again have to assign oxidation states to each element, using the 10 commandments of oxidation states. In this case, magnesium is a free element, so its oxidation state will be 0. In this case, hydrogen is bonded with a non-metal, so its oxidation state will be +1. And chlorine, which is a halogen, we have an oxidation state of -1 due to rule number 8. On the other side, we have a magnesium that is being bonded with chlorine, and magnesium is a group 2 element. So according to rule number 3, it will have an oxidation state of +2. And chlorine is a halogen, so therefore it will have an oxidation state of -1. Because we have 2 chlorine atoms, that will be -2, and as we can see, the charges add up to 0 because it is a neutral molecule. And in hydrogen, in this case, it is alone, so it is a free element, and the oxidation state will be 0. Now we have to look at how the oxidation states of each of these elements changed. Chlorine we see stayed the same, but hydrogen went from +1 to 0. Meanwhile, magnesium had an oxidation state of 0, which increased to +2. If we look back at our rules, oxidation occurs when the oxidation state increases, and reduction occurs when the oxidation state decreases. For hydrogen, the oxidation state went from +1 to 0, meaning hydrogen was reduced. And for magnesium, the oxidation state went from 0 to +2, meaning magnesium was oxidized. Now let's look at another example. Once again, we have to take a look at our rules. Iron, in this case, is a free element, so therefore its oxidation state must be 0. Oxygen always has an oxidation state of -2, and the charge of a neutral molecule is 0, so the oxidation states have to add up to 0. Because we have 3 oxygen atoms with an oxidation state of -2, we subtract 6, and we assign X to vanadium. In this case, we have 2 vanadium atoms, so we assign 2X to it. If we solve for X, we find that the oxidation state is +3. In the other side of the equation, we have iron bonded with oxygen. Oxygen having an oxidation state of -2, and there being 3 oxygens. Because it is a neutral molecule, once again, the oxidation states have to add to 0, and we can assign X to iron, and because we have 2 iron atoms, we write 2X. And solving for X, we find that the oxidation state of iron, in this case, is +3. Here, the oxidation state of oxygen is -2, which should add up to 0. Therefore, if we solve for X, the oxidation state of vanadium should be +2. So now let's look at the oxidation states of each element. Oxygen, as we can see, is always -2. So we don't consider oxygen. But iron and vanadium do change. Iron has an oxidation state of 0, which then changes to an oxidation state of +3. And vanadium initially has an oxidation state of +3, which later changes to an oxidation state of +2. Once again, we refer back to our rules. Oxidation occurs when the oxidation state increases, and reduction occurs when the oxidation state decreases. In this case, iron's oxidation state increased, and vanadium's oxidation state decreased. So therefore, we know that iron was oxidized and vanadium was reduced. Thanks for watching, and I hope you learned something.